Welcome at To The Point, the VideoCast of weColLaborate. And on this episode, coloring, engineering materials and the work of an expert color and analysis of this material group. We are going to talk about where do you use engineering plastics, how are they made, which colors are possible, and how do you do that? Why this topic? Well, there are color specialists and color consultants in many areas, in design, interior, architecture, cosmetics and clothing. But that is usually about which color to choose, the trends, marketing, or the psychology of color. But there is another field where color expertise is of great and daily importance, namely those applications where engineering plastics are used. Material experts and marketing sales departments of engineering plastics generally know how the colors are made and know the importance of a color specialist and colorist. But on average, people do choose a device or car in the desired color or from a specific brand, but are hardly aware of the enormous color and material technology that these products make possible. This is the field of weColLaborate, the advice and ad interim agency for color technology and analysis of engineering materials. We experience plastics everywhere in our daily lives, at home, on the road, in traffic, and at work. Now weColLaborate specializes in engineering plastics or materials. But what are they really? Well, plastics are a very diverse and large group of materials with an enormous diversity of material properties. Roughly, they can be divided into two groups. First, the low-grade plastics, which are relatively cheap for those applications where the usage requirements are relatively simple. The most well-known are polyethylene and polypropylene, which are used in all kinds of home, garden, kitchen objects, and foils. This is by far the largest group with an annual production of about 200 million tons. The second group is the technical high-grade plastics, which also includes engineering plastics. These plastics, which are relatively more expensive, are used in more complex applications, where higher demands are made on the material. About 30 million tons of this are produced every year. In recent years, another group has been added that is an extension of engineering plastics, but has been set aside because of the extremely high processing temperatures, the so-called high-temperature plastics. This group is gaining market share, especially for the new application of recent years, such as parts in electric cars. Think of lamps, high voltage charging systems, and wiring, but also soldering of all kinds of components on motherboards. By the way, this classification undervalues these materials because each plastics, low or high end, is precisely fitting the function for which they are used. Engineering plastics play a role in almost everything we do, use and need in our daily lives, work, recreation, care and safety. Before we go a little deeper into the how and what, can you tell us a little bit about where you use engineering plastics? Do you have some examples? Plenty. Consider the home electrical panel. All fuses are made of engineering plastics. Consider the car. Interior, mirror housing, engine cover, manifold, hoses, tubes, and even the cover for a gear lever. Consider your home, kitchen and garden, your coffee machine, toothbrush, computer, mobile phone, drone, grass cutter, electric saw or drill, and lighting. Consider healthcare, surgical clothing, masks, glasses, and respirators. Consider your home interior, chairs, carpet, or rugs. Consider safety, home alarm system, window frames, motion detector, personal or senior alarm. So the question is more where not to use it. Many plastics have been discovered in the early 20th century, haven't they? All the people and fans of vintage design will know the first plastics. Bakelite, a thermoset. All black for sockets, lamp holders, and even toilet seats. Others, such as polyamide with the nylon stockings and polycarbonate, were also discovered during this period. But it wasn't until after the Second World War that the commercialization and the many uses in our daily life really increased. And then it went very quickly. Why was that? The world was rebuilding. The standard of living was rising dramatically in the Western world, and many and good materials were needed for the increasingly complex applications, and also to replace metals. The engineering plastics, then and now, fully comply with that, because they are, with the right equipment, easy to shape and process. They are wear resistant, can be insulating and protective, strong yet light-weighted, and in all possible colors. The sky is the limit, with seemingly limitless possibilities. We will now go into more details with the question of what does engineering plastics consist of? What is the composition? What is in it? Plastics are compounds, thus a mixture of all kinds of ingredients. But the basis of every engineering plastics, and also the most defining factor for the plastic properties, is the polymer, a long and sometimes complex chain of chemically linked building blocks, the monomers. These polymers are the raw materials we know as polyamide, polyester, polycarbonate, but also polyethylene, polypropylene, and polystyrene. In addition, all kinds of additives are added to strengthen or improve more specific properties, such as fillers, often to lower the price. Flame retardants, very important for electrical components and applications. Fiberglass, to make the material even stronger. Flow improvers, important in processing. And of course, the pigments and dyes. And the follow-up question is, of course, how do you make a mixture of that? How are all those ingredients added together? And subsequently, how do you then turn it into an application or product? All these raw materials are mixed together by an extruder, a beautiful large kneading machine with many feeders that blends all these raw materials at high to extremely high temperatures, from 250 to 450 degrees Celsius. The molten plastic is then cooled and either chopped into small pieces, the granulate, or wound on a spool, the so-called filaments. So the total of polymer and additives we call plastics. Subsequently, the granulate or filaments are melted again to process into any desired shape. The granulate via an injection molding machine or a blow molding machine, and the filaments via a 3D printer. And finally, all those shapes, some of which can also be metallics and ceramics, are assembled into a complete device or object. An example is a lawnmower with injection molded body cover, fuel tank, handles, etc., which are assembled into one whole device with the engine, cables, and tubes. These extruders come in all sizes, from yields of 400 kg per hour to 8 tons per hour for engineering plastics. And these can be complex processes where reproducibility and repeatability is of the utmost importance. But who has these extruders? Who produces engineering plastics? Who can you buy it from? Quite simply, engineering plastics are made by compounders, and they can be both local and global producers, with both one or more extruders, with both low and high yield. Some compounders produce mainly natural and black, but most produce a variety of colors. The large compounders, such as BASF, Lanxess, and Celanese, often not only produce the plastics, but also one or more of the needed raw materials. For example, the polymerization of polyamide and polyesters. Others produce, for example, pigment dyes and master batches, such as Lanxess and Avient. But the majority of compounders purchase the raw material from specialist companies. Consider glass fiber from NEG and Owens Corning, stabilizers from BASF and Clariant, or release agents from Arxada and Evonik. There is plenty of choice. See what happens if you Google it. Good and reliable compounders produce with the highest norms and standards. You can easily recognize them by good documentation, communication, and transparency. There is a material available for every application, and new materials are constantly being added. And not unimportant, with amongst other things, REACH in Europe and the Toxic Substances Control Act in the US, strict requirements are imposed on the safety and, increasingly important, sustainability of both raw material and plastic. In addition, I would like to say, choose wisely. Global versus local. In every region, there are good compounders. And of course, the same applies for companies of injection molding, blow molding, and 3D printing. By the way, you can Google this. And if you need additional advice or some suggestions, please contact weColLaborate. And now, to the core of weColLaborate, color and analysis of engineering plastics and materials. Which colors are possible? There really is no simple answer to this. Are there many colors possible? Yes. Are all colors possible? No. Why? Because the engineering plastics are produced at very high temperatures, from 250 to 450 degrees Celsius, and sometimes even higher. And not all colorants can withstand this. The inorganic pigments can usually withstand these temperatures, but are not strong enough to make all colors. And the organic pigments and dyes, which are extremely strong in color and can produce all the colors, are not or less resistant to the extremely high temperatures. Additional complicating factors include the reactivity of some dyes with the polymer and the enormous influence that some pigments can have on the material properties of a plastic. Ergo, it can be an enormous challenge to develop the requested color. So you have to consider the polymer and the additives, reactivity and temperature, safety and material properties, color nuance and color strength, stability inside and outside, and increasingly sustainability and availability. And I haven't even mentioned process performance, specification, key operating parameters or COPs, analysis, and standardization. Color development and processing is a huge challenge, but a very interesting one.
What colorants are there and who makes them?
Simple answer, lots of suppliers for both pigments and dyes, but also master batches and color concentrates. And nobody supplies the complete portfolio, so you will always need different suppliers. The latter also being important for security of supply. The most important is which plastics are involved. For polyamides, really different pigments and dyes are required than for polycarbonate. This mainly concerns temperatures, processing temperature, and reactivity. Good suppliers generally know in which plastics their colorants can be used, but they do not know everything, and certainly not everything, about your plastics and your applications. Therefore, always perform an elaborate test program for new colorants with the relevant conditions that match your plastics, applications, and customers. Consider the influence of pigments on material properties. Consider the stability during production and in consumer use. Consider the color you have to make. To measure is to know. Now, it is impossible to list in this VideoCast which pigments and dyes and from which supplier you should use for such a large variety of plastics, applications and colors. But if you need support or advice for your specific project or production, please contact weColLaborate.
Just going back a bit to standardization and analysis. How does that work and what is important in this?
Color analysis are performed with a color spectrophotometer. With it, in a standardized way, reflected light of the analyzed plate or grains or powder is converted into the practically usable color values LAB. With these color values, you describe mathematically, as it were, what color you have. For engineering plastics, the most common method of doing this is with injection molded color plaques. But sometimes granulate and powder measurements are also sufficiently reliable. By the way, there are new developments for inline color measurements in extruders in order to continuously monitor your coloring process. This is a good addition to existing COPs such as temperature, torque, and yield or flow. Although color is the most visible material property and very important, there are many other very important material properties that are analyzed, such as tensile strength and E modulus, impact strength, density, flow, and CTI, as well as secondary material properties, such as viscosity and glass content. Crucial for analysis are reproducibility and repeatability. You need to know and trust that your analysis is reliable and that the result really says something about the quality of the produced engineering plastics. And that is only possible if standardized instructions are used, such as those described in all kinds of norms and standards, from ISO, ASTM, DIN, NEN, BSI, etc. Good companies and laboratories have an excellent quality management system and are often guided by, for example, ISO TS 16949, ISO 9001, or ISO 70025.
All this is really not that easy. There are so many different aspects of coloring engineering plastics. So how do you do that? How do you approach it? And what is needed for it?
Well, that is the work of a color expert with knowledge and experience in pigments, dyes, and master batches, polymers, additives, fillers, and reinforcements, color technology, analysis, standardizations, engineering plastics and material properties, stability, safety, and sustainability, compounding and processing, and having a network of suppliers and producers. And not unimportant, having knowledge of the market, trends, the applications, and the customer with its specifications.
And may I add, that is the work of weColLaborate. As freelance expert, advice and help with any color in any engineering plastics and possibly other materials. As ad interim manager, lead the color department or laboratory for a period of time. As a trainer coach, train colorists or color lab engineers on all aspects of color technology and analysis. That is it for this video cast. Thank you for watching and listening, and I hope you found it interesting and enjoyable. Do you also have a question or subject related to color or engineering plastics? Or do you want me to record a video cast with your compounding, injection molding, or 3D printing company as a central theme? Just let me know. If you are curious about engineering plastics, colors, or what weColLaborate can do for you and your company, visit the weColLaborate website or contact us via the email address or telephone number listed on the right. And finally, if you want to receive more video casts like this via LinkedIn, then like my post. And sharing of my post and video cast is appreciated as always.